everyone. In this video, we're going to talk about polynomial functions, and we're going to start off by talking about the graphs of polynomial functions. So first thing we need to know is that for it to be a polynomial graph, okay, there will be no discontinuities. Meaning there's no removable discontinuities, there's no holes, there's no jump discontinuities or infinite discontinuities, so there's no asymptotes on this. Okay, there will also be no sharp turns. So it's not going to look like the absolute value graph, the V. Okay, it's going to be nice, smooth, continuous edges. And then our domain is going to be all real numbers for all polynomial functions. Remember, we say negative infinity to positive infinity in interval notation. So an example of what a polynomial graph would look like, if we quickly draw one right here, okay, it's just going to be a nice, smooth, and continuous graph, something that you've seen before, something like that. Okay, so some common polynomial graphs, okay, is our linear function. So remember, our linear function is just a straight line. Our quadratic function is that U shape. A cubic function is very similar to what you've seen before, like this. And a quartic function, okay, it has maybe about 3 terms like that. And that would be a quartic function. Okay, so now that we kind of know what graphs look like, we're going to talk about the leading coefficient test for end behavior. This test specifically only tells us what is happening at the ends of our graphs. Okay, so there's an important note at the bottom. The leading coefficient test only tells us what the tails of the graph are doing. Okay, it does not tell us anything about the middle of the graph. So this purely only tells us about end behavior, which is why it's the leading coefficient test for end behavior. Okay, so looking at it, we have 2 options on the degree. It can be an even degree or an odd degree. And then for the leading coefficient, it can be positive or it can be negative. So if I'm talking about a positive leading coefficient and an even degree, that's going to be this box right here. Okay. So if I'm talking about this box right here, if my degree is even and the leading coefficient is positive, my end behavior is going to end up going up in both directions. Again, in the middle, we don't really know what's happening, so I'm not going to really draw anything because, again, this only tells us about the end behavior. So our end behavior as x approaches infinity, okay, that would be on this side. That is our right side end behavior. Then our f of x is approaching positive infinity. And then as x approaches negative infinity, f of x, that is this left side, is also approaching positive infinity. Okay. Now, if we still have an even function, but it has a negative leading coefficient, what's going to happen is my ends are going to go down. Okay. So as x approaches positive infinity, f of x approaches blank. That is our right side end behavior. So as we go towards positive infinity, our y's are going towards negative infinity with a negative leading coefficient. Okay, as x approaches negative infinity, f of x approaches blank. That is our left end behavior. So that would also be negative infinity. So even degrees, their end behavior goes in the same direction, either both up or both down. Okay, so an example of an even degree would be like x squared or x to the 4th. Okay, a positive leading coefficient would be like 4x squared. A negative leading coefficient would be like negative 2x squared. Okay, now our odd degrees. When we have an odd degree, like x to the 3rd power, or x to the 5th, or x to the 7th, okay, and our leading coefficient is positive, it is going to end going up, which means it's going to start going down. Okay, so it rises from the left side up. Okay, it goes from the left and it rises on the right. Okay, so we could say it falls on the left, rises on the right. Again, what you need to know is that right side, when it's positive, it goes up. So our end behavior, as x approaches positive infinity, f of x, that is our right side. It is also approaching positive infinity. And then as our x approaches negative infinity, f of x approaches, that is our left end behavior. That is going to be negative infinity. Okay, now if we have an odd degree with a negative leading coefficient, it is going to end going down, which means it starts going up. So our end behavior, as x approaches positive infinity, f of x approaches, it's the right end behavior, so it's going down, so it's approaching negative infinity. As x approaches negative infinity, f of x approaches, that is our left end behavior, okay, and that would be going towards positive infinity. So what you need to know is even degrees go in the same direction. Odd degrees, they go in different directions. Okay, positive leading coefficients for even both go up. Positive leading coefficients for an odd degree, the right side goes up. Okay, and then negative for even, they both go down, and negative for odd, the right side goes down. So let's go ahead and use this test to do an example. So example number 1, determine the end behavior of the polynomial functions below. So we have f of x equals 5x to the 5th minus 3x to the 4th minus x plus 6. What you need to know is what is the degree of this polynomial. The degree of the polynomial. Okay, the degree is the highest exponent. In this one right here, the degree is 5. The degree is 5. 5 is the biggest exponent. Then we need to know our leading coefficient. Our leading coefficient is the number in front of the variable with the highest exponent. So that right here would be a 1. So my leading coefficient is 1, which is positive, which means I have an odd degree and a positive leading coefficient. An odd degree means that my endpoints are going in different directions. A positive leading coefficient means my right side is going up, my left side is going down. Okay, so based on the leading coefficient test, we know our end behavior. So as x approaches positive infinity, f of x is going up because it's the right side, which is also going towards positive infinity. If we look at the next one, as x approaches negative infinity, f of x approaches blank. That is our left side in behavior. That is going towards negative infinity. Okay, looking at our next one, again, we need to be able to determine the degree and the leading coefficient. Okay, so the leading coefficient for this one, you have to look at all of your possible variables and then see what it's going to be total. Okay, so this one is different than A because A only had plus and minus signs. This one, they're being multiplied. So what I need you to understand is that this right here has an x squared. This middle term right here is going to end up having an x cubed. And this last one's just going to have an x to the first. So when we're multiplying x or variables of the same base, we're going to add their exponents. So we're going to add 2 plus 3 plus 1, and that's going to give us an x to the 6th, which means our degree is 6. Okay, our leading coefficient is the number that's out in front, which would be this -4. So we have an even degree and a negative leading coefficient. Even degree means they go in the same direction. Negative means they're both going down. Now we can do our end behavior. As x approaches positive infinity, f of x approaches, that's the right side, that would be negative infinity. As x approaches negative infinity, f of x approaches blank, that is our left end behavior, that is also approaching negative infinity. Okay, so you have to be able to use that leading coefficient test to determine the end behavior of the graph. Now, we have a couple new definitions that you may not have heard before, so we're going to go ahead and talk about them. So we have a turning point. Okay, the turning point tells us the minimum number of zeros that we would have to have, or the most number of zeros we could have. Okay, so the turning point is the polynomial of the degree n has at most n minus 1 turning points, which means it has at most n minus 1's extremas, relative mins, relative maximums. Okay, so what do I mean by that? If I have the polynomial function y equals x squared, that means it can only turn at most one time. It can't have more than one term. Well, if we think about the graph of x squared, okay, the graph of x squared looks something like this, okay, which turns only one time, meaning it goes from decreasing to increasing or increasing to decreasing. Okay, if I had y equals x to the third, okay, and I had some extra stuff, that graph looks something like this, which doesn't look like it turns, but again, it says at most n minus 1 turns. So if you're just given a graph, you can take an educated guess on what the degree is based on how many times it turns. And we'll see what that looks like in an example in a little bit. Okay. Then we have our zeros, which we've talked about. Okay. A polynomial of degree n has at most n real zeros. Okay. So if I have an x squared graph, remember, we can have it crossing twice here, okay? Or we could have it just touching it once. Or we could have something that never touches it, okay? But at most, it can have 2 real zeros if it's x squared. If it's x to the third power, then at most, it can have 3 real zeros. It can't go over 3, okay? Lastly, we have multiplicity. Okay, a factor's multiplicity is the number of times the factor occurs within the polynomial. For example, examine the function f of x equals x squared times x minus 3 times x plus 1 to the 5th times x minus 7 to the 8th. Okay, the factor x minus 3 has a multiplicity, so that's this factor right here. It only has an exponent of 1, so it has a multiplicity of 1. While the factor x minus 7, so this one right here, has a multiplicity of, well, its exponent right here is an 8, so it has a multiplicity of 8. So this x squared right here, what multiplicity do you think it would have? I hope you said 2. Okay, what about the x plus 1? What would its multiplicity be? I hope you said 5. Okay, so why do we need to know the multiplicity? Well, because it helps us when we are graphing. So if we have an even multiplicity, so 2, 4, 6, 8, 10, any even number, okay, the graph is going to be tangent to the x-axis at the corresponding 0. What that means is it's just going to bounce off the x-axis. It's going to bounce and come back up. It is not going to cross at that point. Okay? Something you may also, that may help you would be it kisses the graph. Okay? It barely touches it and comes back up. So if we have x minus 7 to the 8th power, okay, first off, I hope you know that our 0 for that, or our x-intercept, would be x equals 7. So if I have x equals 7 over here, what that's going to look like as a graph is it's going to come and it's just going to bounce and come back up. It's going to be tangent. It's going to touch it at one spot and go back up. Okay, so that's what it means to have an even multiplicity. An even multiplicity. Okay, then we have an odd multiplicity. An odd multiplicity crosses the graph at the x-axis at that corresponding 0. So if I have x minus 3, my 0 for this one would be x equals 3. It has a multiplicity of 1, which means here's my x equals 3. If I'm drawing my graph, it's going to go through that point like that. Okay, so odd multiplicities actually cross the graph. Even multiplicities touch it and come back up. It bounces off of it. So after we've done all of those notes, now it's time to put all of this stuff together. Okay, so we have f of x equals negative 2 x plus 1 times x minus 2 squared times x minus 1 cubed. First off, we need to know the leading coefficient. The leading coefficient is negative 2. Okay, the degree of this polynomial, well, this is an x to the first times an x to the second times an x to the third. So I have 1, 2, 3, 4, 5, 6. So I have a degree of 6. So what this tells me is that I have a negative leading coefficient and even degree. So my ends should both be going down. Now, at most, how many turning points should we have? Well, remember, if we go back up, turning points say it's at most n minus 1. So you take your exponent, or your degree of 6, you subtract 1. At most, we can have 5 turning points. Then it says, what are the zeros and their multiplicity? So how we're going to write this is the first 0 we have is the x plus 1. If we solve that, we get x equals negative 1. And it has a multiplicity of 1. Then we look at our next one. It's x minus 2, and it's being squared. So that x-intercept would be x equals positive 2, and it has a multiplicity of 2. The multiplicity comes from the exponent that it's with. And lastly, we have x minus 1, which would turn into x equals 1, and that has a multiplicity of 3. Okay, so the end behavior based on our leading coefficient test, again, we had a negative leading coefficient and an even degree, so they were both going down. So as x approaches infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches negative infinity as well, because they're going in the same direction. So now what we're going to do is we're going to sketch a graph. It's not going to be perfect, but we need to use the knowledge that we have in order to sketch this graph. So first off, I'm going to start by plotting the zeros. Okay, so I have a 0 at negative 1, a 0 at positive 1, and a 0 at 2. Okay, we're going to use the knowledge of their multiplicities to know that at negative 1, it's going to cross. Okay, at positive 1, it's also going to cross. And then at 2, it's going to have to touch. Now, we have to be going in the same direction, down. So we have to end going down on both of our graphs. And we can have at most 5 turning points. So let's see how we do this. Okay, we have, let me move my graph a little bit, or my lines a little bit. So I have this. So there's 1 turning point, 2 turning points, 3 turning points. We got to turn one more time so we can end up going down. 5 turning points. So the graph might look something like this. It could have less turning points, okay, because we know at most it can only have 5. And right here we have 5. So a turning point would be 1, 2. Oh no, I only had 3 turning points. Okay, so it could have more turning points than what I had. It can have at most 5, but it can't cross the x-axis again. Oh, so I did not graph this right. Let's redo this. I'm sorry. I crossed at 2 and we weren't supposed to cross at 2. So here we go. Let's try this again. I have a 0 at -1, +1, and 2. Okay, they have to end going down. So here we go. I cross, but at 2 I can only touch and come back down. There we go. So it might look something like that. Okay, that was my bad on the first one. Okay, you cannot cross at 2 because it has an even multiplicity. So I have a 0 at -1, 1, 2. It crosses at -1, it crosses at 1, and it just bounces off at 2. Okay, let's look at our last example. Okay, given the graph of g of x, identify the following. Okay, is the leading coefficient positive or negative? Well, that's going to tell us first how it's ending on the right side. So on the right side, it's going up towards positive infinity. So our leading coefficient is positive. The degree, is it even or odd? Well, it's going in different directions, which tells us it's an odd degree. Okay, how many turning points does it have? Well, a turning point would be 1, 2, 3, 4 turning points. So what is the minimum degree that this can be? Well, remember, it's going to be 1, 2, 3, 4, and I add 1, and it's going to be a minimum degree of a 5, which makes sense because it's an odd degree. What is the Y-intercept? The Y-intercept is right here at 0, 0. What are the zeros and their multiplicity? So I'm going to start from the left and work my way to the right. The first 0 we have is right here at x equals -6. And it's going to have a multiplicity of, it has to be even, so let's just say 2 because it's bouncing off. My second 0 is at 0. And it's going to have a multiplicity of, again, it's bouncing, so it has to be even. So let's say 2 again. And then lastly, I have a 0 at +5. And since it's crossing, let's say it has a multiplicity of 1. Well, if I add that up, 2 + 2 + 1 is 5. We said the minimum degree is 5. So again, that's how we can check our work. Okay. What are the local extrema values? Okay, so the minimum values. So on this graph, we have some minimum values. Okay, so let's look. This right here is a minimum at -4. So we have a minimum value. So when x equals -3, there's a min value at -4. Okay, then we have another one right here. So we're going to have to take an educated guess at what this is. So it's about maybe 3.5 for the x value and maybe about 10.3. So when x is about 3.5, the min value is, what do we say, 10.3? Okay, this right here should say is as well. So we state the x value and then we say that the min value is whatever the y value is. Okay, now I'm going to erase some of this graph because it's starting to get a little messy. Okay, so here we go. Next, local maximum values. So I have a maximum here and a maximum here. So when x equals -6, the max value is, what is that y value? 0. When x equals 0, that's the second one right here, okay, the max value is also 0. So we stated the x value and the y value. Okay, lastly, we have in behavior. So as x approaches positive infinity, f of x approaches blank. That is our right side in behavior. So as x approaches positive infinity, our y value is going up towards positive infinity. And then as x approaches negative infinity, f of x approaches blank. That is our left in behavior, and that is going down towards negative infinity. So if you have any questions, go ahead and write them down and make sure you ask me so I can clarify any misconfusion or any mistakes or confusion that you may have. And I will see you in the next video. Have a great day.